In this video lecture, I'm going to be talking about factor analysis, and I'm basing the material that I have here really on 4 different books on factor analysis that I've summarized in this 17-page document, which you can find for the class on Canvas. If you're tuning in from elsewhere, then you don't have access to the actual document. The books that I'm using here as references are all highly recommended. The first is Paul Klein, 1994, An Easy Guide to Factor Analysis, and this is really a great resource. I highly recommend Klein's book for those who want to understand fully how factor analysis works. Also, Robert F. DeVellis's Scale Development. It's a small book, 3rd edition. This is 2012. And this walks through factor analysis, Cronbach's alpha, and other aspects of scale development. And in addition to that, I'm also using information from Petlacky and Sullivan's book, Making Sense of Factor Analysis, also highly recommended. And one last book by Fabriger and Wegner titled Exploratory Factor Analysis. And all 4 of these books covering factor analysis in somewhat different directions, and it's by going through the different books like this that you really get to have a strong sense of how factor analysis works. And so I've sort of pulled together different elements from these different sources. So walking through the handout that I have here, the goal of this handout is to provide you with a computational example of how factor analysis works using principal component analysis. And then I'm going to show you how to do the same thing in SPSS. Well, nobody actually does factor analysis with a calculator. It's useful because you can see what the numbers actually mean, how they're derived, and how they work together. So what we see here is a table of data. These are correlations, and this is a fake data set used strictly for example. I got the example here. The numbers come from Paul Klein's book, and this particular example, if you have his book, starts on page 30. So we see that we have a data set with 4 variables. Excuse me, I'm still recovering from COVID-19. The 4 variables are IQ, verbal, math, and spatial. So we might imagine that this particular data set deals with mental ability measured in a variety of different ways. We can also imagine that each one of these variables, IQ, verbal, math, and spatial, are made up of multiple individual items, and that what we're looking at here is the summated score for a test of IQ, a test of verbal ability, a test of math ability, and a test of spatial ability. So we're treating these as if they're individual items, but we can presume that each one of these is itself a scale, and each one of these is presumably made up of k number of items, where k just simply stands for whatever number of items there is. But we can still take the correlations of these 4 different measurements, and we can still do a factor analysis on these summated rating scales. So again, what we see here is a correlation where IQ correlated with itself is 1, verbal correlated with itself is 1, etc., going down the diagonal. And then IQ correlates with verbal at R equals 0.40, IQ correlates with math at R equals 0.30, etc. And again, this is fake data, so the numbers don't actually represent any real measurements. At the bottom, you see the capital Greek letter sigma, which, of course, in statistics stands for summation. So what we're doing here is we're taking each of these variables along the columns and summing the correlations. 1 plus 0.4 plus 0.3 plus 0.2 equals 1.9, etc. for each one of these. Next, what we need to understand about factor analysis before actually doing it is that the starting assumption of factor analysis is represented in this figure on the left-hand side of the screen, where you have a model that represents a single underlying latent variable. A latent variable is a variable that you cannot measure directly. It's the thing that you're trying to capture in your measurements. And one of the ways in which these things are displayed graphically, one of the important things to understand is that anything that's represented as a circle is not measured directly, whereas anything that's represented by a square, like IQ, verbal, math, and spatial, these are things that you have actual measurements for. But of course, the measurements themselves do not measure the thing itself directly. Rather, the measurements represent the behavior of the person on the thing that you're asking them to do. So you need to understand that up front. But then the other thing is that factor analysis starts with the assumption, represented here in this figure, that it's possible to have a single factor that explains all of the behavior on the different observed variables that you have. So the squares, again, those are the observed variables. The circles are the unobserved variables. On the very left-hand side, you have factor 1, which is your latent variable, the thing that you're trying to explain. And then on the right-hand side of this small figure, you have these circles with E1, E2, E3, E4, and those represent the error of measurement on the scale itself. So you'll have some score for IQ for each person, but that score is that's the actual behavior that the person has done on the IQ test. And assuming that we're trying to measure something innate called IQ, then we're also going to have an error of measurement that goes along with that, because no measurement that we can devise is perfect in terms of capturing everything that we want to capture. Now, the assumption here is that this latent variable called factor 1 is some kind of mental ability that's more broad than simply IQ, that you're also going to be measuring verbal, math, and spatial, that all of these are caused in some way by the single factor. And you can see the arrows of causality going from this latent variable, factor 1, toward the boxes, which is representative of the nature of what we're doing, that we're assuming that the actual behavior on these 4 different scales is caused by the underlying latent variable. So far, so good. And factor analysis starts with the assumption that it's possible that there's one factor and one factor only that is sufficient to explain all of this behavior, but it's also possible that you need more than one factor. So the second illustration here is an illustration of the two-factor model, or a two-factor solution, where the first factor is not sufficient to explain all of the behavior on the different variables that we've measured, and in fact you need to have a second factor in order to capture a sufficient amount of the variance on the things that we're measuring. Each factor captures variance. That is to say, what we're talking about here in factor analysis is that some of the variability on IQ, some of the variability on verbal and on math and on spatial is associated with factor 1, and if there's sufficient variability left over after accounting for factor 1, then you can create a second factor out of the variability that's left over on these variables. As I walk through the computations for the actual example, this part of the nature of factor analysis will become very clear. And you can read the text here on your own. Again, this document will be loaded onto Canvas, so that you have access to it if you're in class. So here's how you would actually compute a factor analysis. And the version of factor analysis that I'm working with here is principal components analysis, which is the easiest one, to my mind, to actually compute by hand. And the way that it works is this. You take the sum of the correlations. So if we go back to the previous page with the correlation table, this is our starting point, the correlations. And we take the sum of each column of correlations. So 1.9, 1.7, 1.8, and 1.8. That's where we start. We take the sum of these correlations and we call that a vector. And so this is the first vector. The sum of the correlations are represented here. You see that I've got a typo here. I'll go back and fix that at some point. I just noticed that. A funny thing. Nobody in classes knows. So yeah, this number here is wrong. The 1.8 should be a 1.6. This one right here. So 1 plus 0.3 plus 0.2 plus rather 0.1 plus 0.2. This should be 1.6. So this number is correct right here. So the next step is that we normalize these vector values. So we take these scores and we normalize them, and the way that this works is that we square the numbers. 1.9 squared is 3.61, 1.7 squared is 2.89, etc. And I'm only doing this at the second decimal point. I don't know if there are third decimals on some of these. There might be. We don't need to worry about being too exact, because this is just for the sake of illustration. We're going to use SPSS to calculate the actual value and see if it matches or if it's close enough to what we calculate by hand. So we take the squared sum of the correlations, and then we sum those squares, and we get 12.3. And then we take the square root of that, and we get 3.51. That turns it back into its original unit of measurement. This is the process of normalization. Then we take the original sum of the correlations for the column from the first correlation table, divide it by 3.51, and we have a new number that gets put into the table for IQ. That's 0.54, and for verbal, and for math and spatial. So these are the normalized scores for the vector, and this is called a trial vector. Now we have these 4 scores set up here. Each value is the normalized sum of the correlations for that variable in the previous table. But we're not done yet. We take the normalized values for the variable going down the columns. So that you see the constant number here, 0.54 for each one. That's the normalized score for IQ. And then for verbal, it's 0.48, and so on. And we multiply it by the number that was in the original correlation table. So the 1, the 0.4, the 0.3, the 0.2, etc., those came from the correlation table on page 1. And so what we're doing is we're taking the normalized scores, multiplying the normalized scores by the original correlations. And after you do the math, these are the values that you get. And this is a transformed set of correlations. Everything here is based on correlations, and so, one thing that should be jumping out at you as I'm talking about this is that factor analysis really is just looking at the table of correlations in a more advanced way. It's dealing with the variability of the items in a different way than what you can see in a correlation table. Okay, so now we take these transformed numbers and we sum them, this time across the rows. In the first correlation table we summed them across the columns, but now we switch and we sum them across the rows, and this gives us vector 2. And now we have the values from this set of scores right here. That's vector 2. And we do the whole thing over again. So we start from the beginning. Each time we do this, it's called an iteration. We take these sum of the values in this transformed correlation table that we have over here, which are we call this now vector 2. We take these numbers, square them, add them up, we get 3.06, and then we take the square root of that. Because they were squared over here, we want to take the square root to turn it back into its original unit of measurement. And it's 1.75. And then we normalize them using the same process as before. 0.97 divided by this number 1.75, 0.85 divided by 1.75, etc. And this gives us trial vector 2. And as I mentioned before, each pass at this process, or each cycle, is called an iteration. In SPSS, you'll see in the output, when you do a factor analysis, it will tell you how many iterations were done by SPSS until it reached its conclusion. And the conclusion happens when there's very little difference, or virtually no difference, between this trial vector and the next one. And when that happens, it's called convergence. That is to say that any further iterations are not going to change the numbers very much at all. That's when you have convergence. At each stage or each iteration, we compare the trial vector that's derived through this process with the previous trial vector, and when there's virtually no difference between them, then the process stops because we've reached convergence. And at that point, then you can calculate what's called the eigenvalue. And the eigenvalue is the one thing that is common in reports of factor analysis. Everybody always reports the eigenvalues because the eigenvalues are the primary way that people use to determine the number of factors. Although it's not the only way, as I'll describe in a minute, or a few minutes. Now, in this actual version right here, using these data, a third iteration is required, but I'm not going to show it here because I don't want to spend time on it. But I did it myself, and you can see the outcome skipping past the next set of computations. The last trial vector, or the last vector rather, would be this, and then square those numbers. You get 3.05. Add them up, take the square root, and it's 1.75, which it's the same as up here. And this is the first eigenvalue. So at this point then, after a third iteration, we've reached convergence. There's no change between this trial vector and the previous one. And so we stop, and that number becomes the eigenvalue. Now, the next thing that you do is you take the root of the eigenvalue, take this number, 1.32, and multiply it against all the values in the first characteristic vector, 0.55 times 1.32, 0.49 times 1.32, etc. And these numbers that you get by this process of taking the trial vector scores and multiplying it by the square root of the eigenvalue, these are what give you the first principal component. These four numbers right here. Now, no one ever does this by hand. People used to have to do this by hand before computers were developed, or at least before they were developed for, I guess, the powerful home computers that were, beginning to be created in the 1980s, in 1990s. That really opened up the sphere for doing factor analysis on an individual basis. Before that, large institutions like businesses, universities, the military, had mainframe computers which could handle some of this stuff, but they were very difficult to use. You had to use punch cards to input the information, and the information was stored on magnetic tapes. It's back in the 1960s. So, at that stage, before you had programs that could actually do factor analysis, people had to do this by hand. And so some of the original research in personality and intelligence testing in terms of factor analysis that was done by psychologists like Raymond Cattell, they did these factor analyses by hand. And it could take a couple of years in order to factor analyze a large data set, because there's so many computations involved, and you had to keep a very clean record of the computations to make sure that you didn't make mistakes. So thankfully we don't have to do that. But you can see how these numbers were derived. Now, one way to think about these numbers, for instance, with the IQ, where we have a loading, what's called factor loading, right here, 0.73, what we can say is that IQ correlates with factor 1 with a correlation of 0.73. Verbal correlates with factor 1 with a correlation of 0.65. Math with a correlation of 0.67, etc. But these are not partial correlations. So you cannot say, for instance, you cannot say that IQ accounts for a certain amount of the variance of factor 1. If you take the correlation and square it, then you have the amount of variance that's associated with something, or the amount of overlap that they have. So 0.73 squared, for example, is 0.53 or 53%. You cannot say that IQ accounts for 53% of factor 1 because these are not partial correlations. You'd have to have a partial correlation in which the other correlations are factored out or controlled for. So there's overlap between these variables, but what we can say is that IQ loads more strongly onto factor 1, and spatial has the weakest factor loading, but it's still fairly decent. So I explain all that here. Now if we were to keep going, we would find out if there's enough variability left after taking these numbers out of the correlation matrix. What we would essentially do is we would determine the loadings for factor 1, and this part of the mathematics is too challenging. I'm not going to do it here. But what we would do is we would use the residuals after removing these parts of these variables that load onto factor 1. Whatever's left over, whatever did not load onto factor 1, we would leave that in the correlation matrix and see if we can make another factor, and then another one after that, and so on. So that's what I meant on page 1. At the bottom of page 1, if I go back up here, where I said that the assumption in factor analysis is that a single factor is sufficient to account for all the variability on the thing that we're looking for. But if the factor loadings are not very high, on that table that I just had on the screen a minute ago, that would be an indication that there's a lot of variability left over that might then be sufficient to create a second factor out of. So each time you do this, each time you identify a factor, you ostensibly you remove the variability that those variables have with that factor from the correlation matrix, and you see if there's sufficient variability left over to create another factor, and then another factor after that, and so on. And when there's no variability left over, then you're going to run out of space for more factors. In factor analysis, a single factor solution is nice, I guess, because it's nice and clean, but normally you don't get a single factor solution. The maximum number of factors is the maximum number of items that you have. So with this data set where we had 4 variables, the maximum number of factors that you would have would be 4 factors. And that would only happen when the items or variables that you have in the correlation matrix have very low correlations with each other. So the higher the number of, the higher the value of the correlations in the correlation matrix, that tells you that there's more variability to work with to create your factors. And normally with with a scale that has 20 or 30 variables, if the variables are correlating well with each other, then it's likely that you'll have somewhere between like maybe 2 and 5, or maybe 3 and 6 factors that evolve out of that. And that indicates something very important about the nature of what factor analysis is supposed to do. The whole purpose of factor analysis is that you take a large correlation matrix that you've derived from a number of items, and you turn it into turn it into something smaller. So let me rephrase that because I'm coughing a little bit. Um, if you start out with a scale that has 20 items, the correlation table is going to be very large. What we would rather have would be a smaller set of factors that represent all of the behavior on those different items. And so if you can boil down the 20 items on a scale to, let's say, 3 different factors, that's a better representation because it's easier to work with. And it tells you can learn something about what those factors are. By looking at the wording of the items, you can identify the themes that the factors are associated with. So it's in SPSS, it's actually called um, data reduction or dimension reduction. So you take the large set of items and you reduce it down or boil it down to its principal components. Think of it that way. I like to think of it as lumps of gravy. I like to think of it as you're boiling down the set of correlations to find out how many clumps there are. Okay, so skipping past some of the text here. The text repeats much of what I just said. Here's an example with actual data. So this comes from the data set that you have on Canvas. I'm not going to go through all the computations here because it's very repetitive with the example that I gave you a minute ago from Paul Klein's book. This is the RWA data set that you have on Canvas, and it's data from an actual study that I did a few years ago. The RWA scale stands for right-wing authoritarianism. It's a scale created by Bob Altmaier. Altmaier is a Canadian researcher. He's retired now, but for many years he was at University of Manitoba in Canada, and he spent much of his career studying right-wing authoritarianism. He started developing the scale back in the late 1970s, and through the subsequent 20 or 25 years, he kept revising the scale to make it better. At one point, it was a 30 or 32 item scale. The first 2 items were what he called table setter items. Most recently, he's boiled it down to a 20 item scale, which is published in his book called The Authoritarians. If you Google right-wing authoritarianism or RWA and Bob Altmaier, you'll find his webpage, and he's got a free PDF of the book available. You can also buy, I think, a print-on-demand version of the book, but off of Amazon. But but you can just download the PDF of it. So the scale itself is found on pages 17 and 18 of Altmaier's book. I've got the scale items right here, so let's take a quick look at that. Our country desperately needs a mighty ruler who will do what has to be done to destroy the radical new ways of and sinfulness that are ruining us. And try that again. Our country desperately needs a mighty one more time. Our country desperately needs a mighty leader who will do what has to be done to destroy the radical new ways and sinfulness that are ruining us. And that's sort of the essence of authoritarianism, that you're looking for a strong leader who's going to stamp out people who we think are deviant. Altmaier envisioned 3 different factors to the scale. Authoritarian aggression in his first item clearly loads onto authoritarian aggression, but he also has authoritarian submission or subservience to the authority powers like the police, and conventionalism. So if we look at the second item here, gays and lesbians are just as healthy and moral as anyone else. A person who's high on authoritarianism is going to disagree with that, so it's a reverse-coded item. You want to have some reverse-coded items when you're creating a scale. Partially because, historically there's been concern about what's called response set, where, people who are highly agreeable are going to be scoring higher on the scale. But also because if you flip some of the items in terms of the direction of the theme of the item itself, it makes people have to stop and think about how they really feel about it. And so it's a good idea to have some reverse coded items. But this item, the theme of this one, is clearly different than the theme of the first one. The mighty leader is definitely different than, the sense of morality revolving around sexual issues. And so the second one, I would say, probably loads onto conventionalism. Um, and you can see that there are a number of different conventionalism items, mostly dealing with sex or things that might be thought of as being sinful. There's absolutely nothing wrong with nudist camps, another reverse coded item. So there are 20 items on the scale, and it's scored using a 7-point scale, sort of the standard Likert type scale, as they say, from strongly disagree to strongly agree. These are called the anchors of the scale. And this would be a 1, a 2, a 3, a 4, 5, 6, 7. So with that in mind, let's go back to the example. These 4 items are from the scale. It's not the entire scale. The scale is 20 items. And it's from an actual study that I did a number of years ago with 421 subjects. I got the data online from volunteers. And if you follow through this, you see how I calculated the vectors and the trial vectors. It's basically the same thing that I did with the previous example, but I'm going to skip the computations here for time. When you examine the document on your own, you can see how the computations are done. But for our purposes, I just want to see if SPSS calculates the same thing that I do. So I'll skip to the point where I get the first eigenvalue. And the first eigenvalue is 2.027. And then I use that, I take the square root of that, and I multiply it by the numbers from the first characteristic vector, the A2, so those are up here. So I take this number 1.424, multiply it by each one of these, and this gives me the factor loadings. So here's the eigenvalue that I calculated by hand. It's right here, 2.027, and the factor loadings are right here. These are the calculations here, and here's what I got from SPSS. So it's pretty close. 0.758 versus 0.753, 0.638 versus 0.629, and so on. And the eigenvalue 2.027 versus 2.025. So I would call that a hit. It's just a little bit of rounding error at the third decimal point, which is trivial. Now let's see how we actually do it in SPSS, and the data set itself is loaded onto Canvas for you. Here's the data set. Let me move that a little bit to fit into the screen. So we can see that we have our RWA items. If we scroll down, we see that we have lots of subjects, 400 and some, and there are 20 total RWA items. I deleted the other variables in the study because I just wanted to use the RWA scale. So what we're going to do is we're going to factor analyze just those 4 items. And this is where you find the pathway. Actually, let me increase the magnification on my screen here, which will make it a little bit easier to see in the video. I've got to move the SPSS now. If I can get it right. Hang on 1 second. Now this is okay. So there I've resized things to make them fit onto the screen. So here's my data set, and to do a factor analysis, what I do is I open my Analyze menu, scroll down to Dimension Reduction. That's the option for factor analysis, and here's the factor analysis. When you click that, you get a pop-up, and we see the 20 items. We only want these 4 items, number 15, 16, 17, and 18. take them over. You can highlight them all at once. Take them over here, and we want to check out our options. Right now, I'm not going to talk about these options, the reproduced, anti-image, and KMO, but I will later. Right now, I just want to check the extraction menu and the rotation menu. For extraction, you can see that the default setting is principal component. That's the one that I did by hand. When you open that up, when you open that menu, you see that there are a number of other ones as well. But for right now, we're going to stick with principal components because that's the one that I did by hand. Let's take a look at the scree plot. So check scree plot, hit continue, and then click the rotation button. You can see that none of them are selected. And that's fine for right now because I just want to check to see if my raw factor loadings are the same as what I calculated by hand. So we're not actually going to rotate the data here. We're just going to run a principal component analysis in its so-called vanilla version. So we run that, and here are the extractions. But that's not the part that actually matches up to the calculations. If we scroll down, we see the component matrix. And so now we have the unrotated principal component analysis, and that is the part that I computed by hand. So we get the loading of RWA 15 onto factor 1 at 0.753, and if we go back to the document, that's where this number right here comes from. So that's the way that you do this in SPSS to find the same numbers that I did by hand. And then the other thing is the eigenvalue 2.207. So let's go back to the output, scroll back up a little bit, and SPSS tells me that the output is 2.025, and I computed by hand 2.027. The other thing to point out here is the first factor. The eigenvalue identifies the first factor. The first factor explains 50.615% of the variance of the correlation matrix. And then you can see that it has a second factor where the eigenvalue is greater than 1. Having an eigenvalue greater than 1 is the primary rule that people use to identify the presence of a factor. But as a secondary rule, you also want to have the percentage of variance explained at 5% or more, and we can see that these are both much greater than 5%. So you have to have both of these in place, an eigenvalue greater than 1 and a percent explained at 5% or more. So the first factor explains a whole lot of the variance, about half of the variance in the correlation matrix. What the program does then is it takes out that variance and it sees if there's enough left over to factor another clump out of the data, and there is, with an eigenvalue greater than 1, and that one accounts for 26.628% of the variance. Now we've taken out all of that variance, 77.243% of the variance. Whatever's left over, whatever residuals are left after removing that variance from the correlation matrix, it's not enough to reach an eigenvalue greater than 1, so that's where the process stops. This third one is not a factor, and the fourth one is not either. Now the scree plot illustrates much of the same thing, but it's kind of hard to interpret here because there are only 4 variables. Usually you have more, but the way that you interpret it is that the bottom down here, where you see a kind of a flat line almost, that's called the scree, and scree is the rocks and rubble that accumulates at the bottom of a mountainside. So the way to think about this is the mountainside and the rubble. And the rubble is not a factor. Well, the rubble stops here and the mountainside begins. That's where your factors are. So from this dot, that's a representation of the first eigenvalue. From here to here is one factor, and from here to here is a second factor. and then it stops. And so this scree plot is in agreement that there are two factors, where this would be the first factor, this would be the second factor, so all of our criteria, our three criteria for identification of factors, are in agreement. You have to have an eigenvalue greater than 1. It has to explain at least 5% of the variance, and the scree plot has to be in agreement with a number of factors. So according to all three of these criteria, there are two factors in this matrix. So that's how we interpret these scores, and it's a very basic version of factor analysis. Okay, so we go back to the document. Actually, let me make my screen smaller again. Make it normal sized. There we go. Actually, I'm having some mechanical difficulties with my recording program, so I'm going to stop this here, and this will be part 1 of 2 parts, and I'll pick up at this point in the second part of this video. So please, if you're following this, then when you get to this point, open up the second video.